To escape the limitations of fossil fuels, humanity is attempting something that sounds like science fiction. We are building a functioning, literal star on Earth. Current nuclear plants rely on fission, releasing energy by breaking heavy atoms apart. Fusion takes carefully opposite approach, forcing small atoms to merge. This generates immense power without the long-lived radioactive waste. Look at the sheer scale of the solar flares here. This exact process of atomic merging is what powers the real sun, and mastering it would provide a near-infinite source of carbon-free energy. But there is a massive physical problem. The sun triggers this reaction using its immense crushing gravity. Here on Earth, we don't have that cosmic weight to naturally squeeze atoms together. To compensate for the lack of gravity, scientists substitute pressure with raw heat. We must heat hydrogen matter to over 100 million degrees Celsius. That creates a fire hot enough to instantly melt any material known to man. This is the tokamak. It's a specialized, donut-shaped vacuum chamber designed to handle that extreme environment. When you heat hydrogen fuel to 100 million degrees inside this machine, it stops behaving like a normal gas. It transforms into plasma, where electrons are stripped from nuclei. Because physical metal would vaporize on contact, the reactor uses an invisible cage. Superconducting magnets generate a field that suspends the roaring plasma midair. But holding a miniature star inside a magnetic net begs an obvious question. What if the power cuts out or the magnets fail? Does the facility explode? A natural star is held together by gravity, which constantly crushes inward. An artificial star, held up entirely by magnets, naturally wants to expand and cool down. If there is a single microscopic error or a power drop, the plasma instantly loses its heat and the reaction stops. This makes fusion difficult to sustain, but it also makes it a self-terminating process that cannot result in a meltdown. Securing this power has triggered an active global race. Nations are currently competing to hold that plasma stable for longer and longer intervals. South Korea's K-Star reactor and China's East facility have both broken records for plasma duration, proving the engineering is finally catching up to the physics. Yet one massive scientific roadblock remained for decades. Running these colossal magnets and heating systems required more electricity than the fusion reactions actually produced. This chart illustrates the milestone that solved the math. At the U.S. National Ignition Facility, scientists finally generated a fusion reaction where the energy output surged past the energy required to trigger it. While it wasn't a grid-ready power plant, achieving a gain in energy proved that a self-sustaining artificial sun is a practical possibility, not just a theoretical one. The scale required to turn those experiments into a working power station has pushed 35 nations to pool their resources into ITER. This facility in France is a massive collaboration designed to coordinate thousands of independent systems into a single working reactor. Constructing a machine requiring advanced cryogenics, ultra-powerful superconducting magnets, and radiation-resistant materials demands resources and microscopic precision no single country can manage alone. With China, Japan, and Western nations developing massive independent reactors, one major player appears absent from the headlines. Why hasn't India built its own full-scale artificial sun? India has chosen a calculated path. Instead of rushing a solo megaproject, Indian scientists are integrated into ITER, building critical components for the French facility, while simultaneously running their own ITER reactor at home to train specialists. They are executing a learn-first, build-later maneuver. By mastering extreme frontier engineering through global partnerships today, India is laying the groundwork to build its own independent fusion network between 2030 and 2050. For 2 centuries, human progress has been tethered to finite, carbon-heavy fuels. Fusion offers an alternative that is both clean and virtually inexhaustible. A global grid powered by the heavy hydrogen found in seawater could dismantle the influence of oil monopolies and permanently end resource-based energy conflicts. A clean energy surplus changes our approach to the planet, providing electricity for massive water desalination and the heavy power requirements of future space missions. Fire gave us civilization, electricity modernized it, and if we can successfully bottle the energy of a star, we may finally stop worrying about where our power will come from.